Hello class, welcome to this video on 6.3 part 1. Let's look at that first, the first question here. Alright, so we want to describe a binomial setting. Okay, so does this scenario describe a binomial setting? And explain. So biologists estimate that a randomly selected baby elk has a 44% chance of surviving to adulthood. Assuming this estimate is correct, suppose researchers choose 7 baby elk at random to monitor. Let x equals the number that survived to adulthood. All right, and then we're going to see if this follows Binns, right? So Binns for binomial setting. So is it binary? So I'm going to say binary. In this case, we have, yes, we have success is survival, or survive. Failure equals does not survive. All right, and we got, is it independent? And the answer is yes. Knowing one elk outcome doesn't affect another elk's outcome. In other words, they're independent. Number of trials, is the number of trials fixed? In this case, yes, right? We have, in this case we have n equals 7, and then last, do we have the same probability? And the answer is yes, we have a probability of 0.44 to survive. Probability of success. All right, so in this case, each of these, so yes, we have a binomial, so yes, x is a binomial random variable. All right, so let's look at a second one. Put the names of all the students in your statistics class in a hat, mix up the names, and draw 4 without looking. Let x equals the number whose last names have more than 6 letters. Okay, so in this case we have, okay, so so binary. In this case, yes, we have either the name has more than 6 letters, right? So name with greater than 6 letters versus name not greater than 6 letters. Okay, so that's binary. And then we have independent. Well, in this case, it fails independence. It fails independence because we are selecting without replacement. So no, we are selecting without replacement. Since we're selecting without replacement, it's going to change the probability of the next event occurring. So if I draw one name, that's going to affect the probability of the next name being drawn, and therefore it's not independent. And then we have number, and the number here is constant. We have 4 trials, right? And then same. In this case, yes, the probability of success for a particular trial is the same, right? And we're talking about for a particular trial. This is the unconditional probability, okay? So the unconditional probability of a given trial is the same. Okay, so even though the probability may vary if you're selecting 4 names, if you're looking at the unconditional probability, meaning no conditions, meaning you're just think of it as a regular selecting with replacement, the probability of a given trial is the same. However, we know that it's not independent, and so that it fails that. All right, so then that means x is not a random variable, a binomial random variable. Okay, all right, so number 3, does this scenario describe a binomial setting? Lawrence likes to shoot a bow and arrow in his free time. On any shot, he has about a 10% chance of hitting the bullseye. As a challenge one day, Lawrence decides to keep shooting until he gets a bullseye. Let y equals the number of shots he takes. Okay, so let's see, is it binary? In this case, he either makes it or a bullseye or not, right? So bullseye or so x is the number of shots. Yeah, let's just call it the hits, right? So number of hits. Okay, so hits slash does not hit. All right, and then we have independent. Is it independent? Yes. In this case, one shot's outcome doesn't affect the next. All right, and then n number. Are the number of trials fixed here? Well, it says he decides to keep shooting until he gets a bullseye. So this is not a binomial setting, right? So in fact, now that we've done the entire lesson of 6.3, this is actually a geometric distribution because we don't know. He keeps shooting, right? We don't know what that number is till he gets the bullseye. So in this case, the number of trials is not fixed. And then so it fails that. And then same probability. Yes, the probability is 0.10 to hit. So that's true. That's okay. But since it fails one of these, that means y is not binomial random variable. Okay, so let's take a look at the next problem set. The next problem set is about calculating probabilities for a binomial random variable. So number 1, Pedro drives the same route to work on Monday through Friday. His route includes one traffic light. According to the local traffic department, there's a 55% chance that the light will be red on a randomly selected workday. Suppose we choose 10 of Pedro's workdays at random and let y equals the number of times that the light is red. Explain why y is a binomial random variable. Okay, so first off, binary. Yes, right? So we get success is getting red, right? So success is red. Let me do that here, okay? And failure, so failure is not red. Sorry, not red. And independent, each light's outcome doesn't affect the next. So that's true. And then number, the number of trials, we have 10 work days. So fixed, right? So that's good. And then same probability. And the answer is yes. The probability is 0.55. Okay, so therefore it's a binomial random variable. So it satisfies all these. Okay, so find the probability that the light is red on exactly 7 days. So, all right, so remember the formula for the binomial distribution for binomial probability is n choose x times p to the x power times 1 minus p. Okay, let's see here. 1 minus p raised to the n minus x power. Okay, so there's your formula. And then we have, so we're going to use it. So let's see, we got p of x equals, excuse me, got p of x equals 7, and then we got 10 trials. Remember, n is 10, so we got 10 choose 7. Probability of success is 0.55 raised to the 7th power. 1 minus 0.55 raised to the 10 minus 7th power. And then we can calculate this directly, or we can use the binomial PDF function. Okay, so we got binom PDF function of the number of trials, n equals 10, the probability of success, which is 0.55, and the x value of 7. Okay, and then we can do that and get an answer. All right, we're going to show you on here how to do it. So again, you go to second vars. Oops, let me go back to it. Sorry. Let's scroll all the way down. We got binomial PDF. PDF is for a specific value. So we got 10 trials, 0.55, and I believe it was 7 for the red lights. All right, and then 0.166. All right, so you got 0.1665, okay? And then we're gonna show you how to calculate this on the calculator, just in case you're curious. Not that you have to do that, but I like to teach you the various skills, not just one way of doing it, right? There's multiple ways of doing this. And if you wanna calculate this directly, you can do that. And I will show you how to do just that, okay? Just so that you can learn different ways to do it. I'm going to do this off to the side. Okay, so the formula that we got here for P of 7, we said it was 10 choose 7. Now 10 choose 7 is the same thing as combination of 10 objects taken 7 at a time. So that's 10 choose 7, or the combination. And then we got 0.55 to the 7th power, and then 1 minus, of course, that to the 10 minus 7th power, or 3. And so you can calculate this and then calculate that. You can also use the formula 10 factorial over 7 factorial times 10 minus 7 factorial for this part, okay? And then, of course, you have the 0.55 and all that good stuff, right? All that, in order to calculate it. Okay, so, and then 1 minus to the 3rd power. All right, so let me show you how to do the factorial and as well as the combination. All right, so I'm going to show you how to do both. All right, guys, so we're going to show you how to do it on here. So we got, okay, so in order to do the combination, we have to, so let's go to math and then probability, PRB. And you see the factorial symbol there for 4. So that's how you can do the factorial, but this is the NCR. So first we want the combination of 10. So we want 10 and then choose 7, right? So 10, and then we got to go to math again, go back to probability. And then we got that 10. Oops, I chose the wrong one. Let me delete that. So 10, choose 7. Which is 120, and then you can multiply that by 0.55 raised to the 7th times 1 minus, you could do 1 minus 0.5 if you want, raised to the 3rd power, or to the 3rd power. All right, and you get the same number, see, 0.166. And then if you want to do in terms of factorials, I'm only going to do the 10 NCR7. I'm not going to do this 0.55 because we already know it's going to be the answer. But I want to show you that 10 choose 7 is equal to 120 when we use the factorial formula. So we got 10 factorial number 4 divided by parentheses 7 factorial. Go to math, probability, factorial. Times 10 minus 7 factorial. But 10 minus 7 factorial is just 3 factorial. Okay, so I'm just going to put 3 factorial there. All right, there you go. All right, and there you go, 120 ways. So you get the same thing, but you don't have to do the factorial. I just want to show you this to expand your knowledge. Later on, and in future courses, you might use factorial, especially in maybe in calc and things like that. So you might use the factorial function. And so I just want you to be aware of what that is. So the factorial function is just you take the number and multiply it by itself, or you multiply successively lower numbers all the way to 1. So 4 factorial will be 4 times 3 times 2 times 1. So if I did 4 times 3 times 2 times 1, that's going to be 24. And then if I do the 4 factorial, you'll see I get the same result. So it's a useful function when you have shortcuts to do like that, right? And there are some situations where you need that. Okay, so we showed you a few ways to do that, to calculate that. So now we're going to just focus on we're going to show you the work for this, but we're only going to use the binomial PDF, okay, when we do the calculation. All right, so number 2, an online spinner has 2 colored regions, blue and yellow. According to the website, the probability that the spinner lands in the blue region on any spin is 0.80. Assume for now that this claim is correct. Suppose we spin the spinner 12 times and let x equals the number of times it lands in the blue region. Explain why x is a binomial random variable. All right, so it is a binomial random variable if you use bins, right? So let's talk about that. Okay, so binary. It's either in the blue or not blue, right? So yes is binary. And then we have independent. So independent, one spin doesn't affect the next, right? So one spin doesn't affect the next. So yes, it's independent. Number of trials, we're spinning 12 times, n equals 12. Same probability, let me just do that here. And the answer is yes, p is equal to 0.80, okay? All right, so part B, find the probability that exactly 8 spins land in the blue region. So since we know it's binomial, probability of x equals 8 is equal to, we have 12 spins, choose 8 times 0.80 raised to the 8th power, 8 successes, and then 1 minus 0.80, which is 0.20, so I'm not going to write that here, okay? 0.20 raised to the 12 minus 8 power, which is to the 4th power, okay? All right, so then this is the same thing as binomial PDF, n equals to 12, p equals to 0.80, and x is equal to 8. All right, when you do that, you get 0.1329. All right, so let's look at the next problem set. So now this time we are calculating binomial probabilities using the CDF function, the cumulative distribution function. So that means we're doing probabilities for greater than, less than, rather than exactly equal to. So using Pedro's example, calculate p of y is greater than or equal to 7. All right, remember for Pedro's example, there were 10, let me see, I'm trying to remember. Yeah, it was 10 lights. So n is equal to 10. And then the probability of success for the red lights was 55%. All right, and then y was the number of red lights. Okay, so p of y greater than or equal to 7. remember that to do y is greater than or equal to 7, that means we're doing for 7, then for 8, then for 9, then for 10, right? So we can use the binomial distribution function 4 times, right? 7, 8, 9, 10, or we could just use the binom CDF function. That's what we're going to do here. Okay. All right. So we're going to do 1. So the opposite of greater than or equal to 7 is less than 7, right? So we're going to do 1 minus the probability that y is less than 7. Let me just fix that there. And so remember, the binomial CDF can only be used for less than or equal to. So it's going to be y less than or equal to 6. All right, so and in this case, we have 1 minus, now we can use the binomial CDF function. Okay, so the CDF is going to be n equals 10 trials, p equals 0.55, and x equals 6. You're going to use 6 here, okay, for the binomial CDF function. And you get 0.2660. All right. So now let's do the spinner example. The spinner example, recall, n was 12, and I believe the probability of success was 80%. Yeah, so now we want the probability that x is less than or equal to 7, so we can just use the binomial CDF function because it's already less than or equal to of n equals 12, p is 0.80, x equals 2, not 12, 7. All right, and then you would get 0.0726. All right, so we're wrapping this up. So now we're in the last problem set here. So the last problem set is about calculating parameters of a binomial distribution, such as the mean, standard deviation. All right, so we have a couple questions here. So the number one, the thousands of travelers pass through the airport in Guadalajara, Mexico each day. Before leaving the airport, each passenger must go through the customs inspection area. Customs agents want to be sure that passengers do not bring illegal items into the country, but they do not have time to search every luggage. So they require the person to press a button. A red or green light bulb lights up. If the red light flashes, they'll be searched. If it's green, they'll go ahead. So it says the probability that the light is red is 0.30. Assume for now that this claim is true. Suppose we watch 20 passengers press the button. So we got 20. Let R equals the number who got a red light. So calculate and interpret the mean of R. All right. So, so first off, does this satisfy bins? Let's practice that. Okay. So we got bins. Is it binary? Well, it's either they got a red light or they did not, right? So yes. Is each person independent from one another? Yes. As far as the lights, they're independent from one another and the people. Number of trials fixed. Yes. 20 passengers. N equals to 20. And so let's write that here. So N equals to 20. Probability of success, is it the same? Yes. It's a 30% chance for red. All right, so it's binomial, so we can use a binomial formula. So now we know it's a binomial, so we can calculate the formula, the expected value or the average of the binomial distribution, which is NP, which is 20 times 0.30 in this case. So 0.60. Or no, is it 0.6? No, I'm sorry, 6, not 0.60. 6. All right, so let's interpret that. I really shouldn't have written that big here. So let me make this smaller. Oops, sorry. Let me try it again. Let me try that again. Let's see here. Okay, so that's better. Okay, so let's write down the interpretation. Okay, so for the interpretation, we want that after many randomly selected, right? So we have to include the law of large numbers and include an element of randomness. Okay, so let's see. If many, I need to switch this to the pen. Okay, so if many passengers, or if many, I guess we could say groups. If many groups of 20 passengers were randomly selected, the average number who would get red light is about 6. All right, so there's your interpretation. So now let's calculate the standard deviation. So standard deviation, sigma r, is the square root of np times 1 minus p. So we get the square root of 20 times 0.30 times 1 minus 0.30. So you get about 2.049. So let's interpret that. Sorry. If many groups of 20 passengers were randomly selected, the number who would get red light would typically vary from the mean of 6 by about 2.049. Okay. All right, so let's do the same thing for number 2. Federal report finds that lie detector tests were given to truthful persons have a probability of 0.2 of suggesting that the person is deceptive. Let's ignore these. Ignore that 11 there. A company asked 12 job applicants about deaths from previous employers using a lie detector to assess their truthfulness. Suppose that all 12 answer truthfully. Let y equals the number of people whom the lie detector indicates are being deceptive. Find the probability that the lie detector indicates that at least 10 of the people are being honest. Okay. So bins. Let's just review binary. True. Either it indicates that they're being honest or it indicates that they're not being honest. Each person is independent from one another. N, the number of trials is, we have 12 job applicants, so the number of trials is constant. S, the probability of success is, in this case, to indicate that they're being honest, the probability of success is 1 minus 0.2, so 0.80, because it says 0.2 that the person is deceptive. That means if they're being honest. In this case, 0.8 that they're being honest, and it's the same for each person. Okay. Okay, so we want the probability that y is greater than or equal to 10, at least 10 people, right? So that's 1 minus the opposite of that is that it's less than or equal to, that is. So we get, or no, just less than, I'm sorry, less than or 10. The opposite of greater than or equal to is 1 minus that it's less than, which is the same thing as 1 minus that it's less than or equal to 9. And so we can use the binomial CDF. All right, CDF can only work for less than or equal to. So N, we have 12 trials. probability of success is 0.8, and then X is 9. Okay, and when we calculate that, we get 1 minus, well, we can get the number, so 0.5583. So if I do 1 minus, I get 0.5583. Okay, so now let's do mu y. So mu y is n, which is 12 times p. Okay, so we got 12 times 0.8. Let's see here. I'm sorry, not 0.8. This is a tricky question because it's saying find the probability that at least 10 of the people are being honest. So we actually, I shouldn't be using y here, guys, because we want them to be honest. So we're gonna say x is the number of people that are being honest. Okay, number of honest. Okay, number of honest. So then this should be x, not y. Y is being deceptive. X is being honest. Okay, it makes a difference because if you don't label it correctly, you're going to run into trouble when you do this, because this one's asking for mu y. Mu y is being dishonest. So in this case, your p here is 0.20. Okay, so we gotta be careful. This is why we want to label the variables correctly. Okay, so because it leads to issues like this. So we got 12 times 0.2 is 2.4. So 2.4 people we would expect to be dishonest, right? On average, if you many people, groups of 12 people are randomly selected, right? Oh yeah, so we have to interpret it. So let's do that now. Okay, so if many groups of 12 people randomly selected, average number who are indicated as being deceptive is approximately 2.4. All right, so calculate and interpret sigma y. So let's do that real quick. So this is the deceptive. So remember, p is 0.2. So 12 times 0.2 times 1 minus 0.2. Times 1 minus 0.2. Let me just put 0.2 there. All right, and this is 1.39. Okay, so in this case, it's not letting me type here for some reason. Okay, so if many groups of 12 randomly selected the number indicated deceptive typically or vary from the mean of 2.4 by about 1.39. All right, that's going to do it for the video, guys. Hope you found this useful. I'll see you in the next one.